Hi, my name is Jim, and the topic for today is DC series circuits. And when we have a series circuit, what the common parameter is, I guess I'll call it a parameter, is the current. The current's common, it flows through everything, even though the voltages across the different components of the circuit may be different. Now we're using static resistors here to demonstrate this, but in reality, these could be, say, load resistors associated with a transistor where the voltage of, say, an audio source would be appearing across it. So we're going to be using models that may not make sense, but it's the underlying analytical theory, which is very, very important. So if we're looking at this, as what we see is we have a 6.5 volt battery and a ground reference here, and the ground reference on your car is basically the chassis. So it's a common point that you reference when you're measuring voltages. As the current flows through here, we have node A, node B, and node C, and node D, which is ground, and we're going to be referring to these nodes when we talk about the voltage drop across specific parts. So when the current flows from this 6.5 volt battery, it'll flow out of the positive terminal of the battery, and remember that this is conventional current flow and not electron current flow, and through these resistors, making a complete circuit. That is, there has to be a path of conductors around in a loop from the positive side of the battery to the negative side of the battery. Now, as opposed to the current being the common component in a parallel circuit, it's going to be the voltage. So it's going to be exactly opposite. Now, what we note in here is what we call Kirchhoff's voltage laws, and it's very important to understand this. And what this says is the sum of the rises, this is uppercase sigma, is equal to the sum of the voltage drops. So if we draw our current here, and the current goes from negative to positive, that's considered to be a voltage rise. And if it goes from positive to negative, that would be considered to be a voltage drop. And I'll just put one drop across the resistor here. Further, what we say is the voltage drops in the circuit have to be equal to the voltage rises. In other words, all of the voltage has to be accounted for. We can't leak any place. So we can find the component parameters by finding the current, and what we'd be looking at here is the voltage drops across each resistor. Now, the word drop may or may not reference ground, and that's a very important concept to understand. So what we're going to do here to start with is to find the total resistance, and in a series circuit, it's just going to be the sum total of all the resistors. So we have the sum here, 220, 470, 560, comes out to be 1.25 kiloohms. Now to find the current flow, and using Ohm's law, it's I equals V over R total in this case. 6.5 volts divided by 1.25 K gives us a current flow of 5.2 milliamperes. So once we know the current, a whole lot of different things are going to become available, such as the voltage and the power dissipated by the resistors and the power supplied by the source. So on that page, we had a little bit of KVL and certainly Ohm's law. So let's find out what the voltage drop is across each resistor here. So we could say that V resistor 1 is equal to the value of the resistor times the current flow, 5.2 milliamperes. And your calculator should be an engineering notation to do this. You have to pay attention to the milliamperes, or you're going to be off by a factor of 1,000. And that comes out to be 1.144 volts. So if I took a voltmeter and I went across this resistor, that is what I would measure. That's the voltage drop. It does not reference ground. Secondly, what's the voltage drop across VR2? Again, Ohm's law, R times I gives us 2.444 volts. And we would expect that this voltage would be larger than this voltage because the 470K resistor is larger than 220 ohm. The 470 ohm resistor is larger than 220 ohms. Lastly, we need to find a voltage drop across VR3. Again, Ohm's law gives us 2.9 912. So let's do a little check on the Kirchhoff's voltage laws. Let's add up the sum of the drops here. That would be these guys, and what that comes out to be is 6.5 volts. Notice that the source is 6.5 volts. So the sum of the rises, and we only have one source in this, 6.5 volts is equal to the sum of the drops. That would be the sum of all the voltage drops across the resistor is also 6.5 volts. Now, when you're working with real numbers here, it may be slightly different, and you have to accept the fact that there's going to be errors because of round off and things like that. So, close many times is good enough, and realistically, the tolerance on a typical resistor is plus or minus 5%. So, I have to keep that in mind. So we know that. We know the voltage drops, and let's see if we can find out what the power dissipation is. That's kind of an important thing. So since I know the current and I know the resistance, I elect to use this equation, I squared R. Now there's three different power equations. There's V times I squared times R, and V squared divided by R. And since I've got all here, I'm going to use I squared R. So squaring 5.2 milliamperes, and remember that this is e to the negative 3 when you square it, multiplying it by 220 gives us a power dissipation of 5.95 milliwatts. Doing PR2, same deal here, 12.71 milliwatts. And finally, with the power for resistor number 3 here, comes out to be 15.14 milliwatts. Now, this is dissipated as heat. Now, a resistor has a given rated power. So if these are rated at 250 milliwatts, say a quarter watt, we're in no danger of burning the resistor up. And that's one of the things you have to keep in account is, are you exceeding the dissipation of the resistor? So we're not. So the total power here is going to be the sum total of the power in all of the resistors, and that comes out to be 33.8 milliwatts. So that's the total dissipation, and in the case of resistors, that's electrical energy that's being converted into heat. Now the power supplied by the source, well, we have 6.5 volts, and the current flowing through here is, as before, 5.2 milliamperes, and if we multiply those two together, we see that the source is providing 33.8 milliwatts. So this makes sense. The resistors are dissipating the same amount of power that the source is providing. Like with voltage and with current, all the power has to be accounted for. It can't leak off somewhere. So let's take another look at this. We pushed currents before, and that worked out very well, but sometimes that's very inconvenient to do. And coming up in AC circuits, which is basically DC circuit laws with complex numbers, it's an extra step that involves complex numbers, and if there's an easier way to do it, you need to take it. And that easier way is called voltage divider. And the only reason this works is because Ohm's law is linear, because resistors are linear. Some devices, like diodes and transistors, are very nonlinear, and we'll take a look at a diode a little bit later. So let's become familiar with voltage drop, and it's basically saying VR1 is going to be equal to the source voltage, VI that I've named it, times the ratio, the resistor that we want, divided by the total resistors, comes out to be our 6.5 volts. I want the voltage drop across a 220 ohm resistor. I know from previous calculations that the total resistance was 1.25K, and that gives me 1.144 volts, the same as I got before. VR2 is the same thing, only now in the numerator we have 470 ohms, and then the voltage drop across our R3, 560 ohms, same thing, except the numerator is now 560. If we add up all these drops as before, we end up with 6.50 volts. Again, the sum of the drops is equal to the sum of the rises. Calculating the power now, well, I could find a current, and let's just say I didn't before. But since I have the voltage and I have the resistance, it seems easier to remember that P is going to be equal to V squared over R. in this case R1, because I'm interested in the power across that. So I just take the voltage that I calculated, square it, divide it by 220, and I get, as I got before, 5.95 milliwatts. Same is true for PR2. Got the same thing before when we multiplied the I squared R, and with PR3 got the same power there. And if we add these up, that would be my dotted blue line. It comes out to be 33.8 milliwatts total power dissipation, exactly what we would expect. So in summary here, when you're dealing with power, you have three choices. V times I squared R, or V squared over R, and you need to absolutely know and be comfortable with those three forms of power dissipation. So here we're going to be looking at the voltage across different nodes. And what I want to do in this case, instead of finding the voltage drop across one resistor, is to find a voltage drop across the nodes VAC. Now, you can add these two voltages together to get that given. However, let's take a look at a mathematical way. Suppose we didn't have the individual voltages and we want to get that in one clean step. So using voltage divider here in the numerator, and this only works if the resistors are next to each other, would be R1 plus R2 divided by R total again, and what we get is 3.588 volts. And then if we find VAC by decomposing a doubly subscripted variable. Now everything we measure has two subscripts. Here I have B, so VB sounds like a single subscript. Whenever you have a single subscript, the second subscript isn't written down, it is assumed to be ground. So if I said what's VB, the voltmeter would be across ground and B. So that too is a doubly subscripted variable. So when you decompose a doubly subscripted variable, VA to C is VA minus VC. 6.5 volts would be the source voltage, and we're subtracting from that 2.912, and what we end up with again is 3.588. What's the 2.912? And that's the voltage drop across R3. And that'll give us our voltage. Now, let's find VCA. Why would I want to do that? And the question is sometimes you don't know that you're going to have a positive number. And it doesn't matter, because the math is going to work out and make the answer come out right no matter what. We compose this in the same way. Decompose it. We take VC and subtract from it VA, 2.912, the voltage across this guy. Subtracting from that 6.5 volts gives us negative 3.588. So all that would basically mean is that we reversed the leads on our meter. We had the positive lead here and the negative lead here. So when you're dealing with doubly subscripted variables, sometimes it'll come out to be negative, sometimes it'll come out to be positive. But it doesn't matter when you integrate it into the whole problem. Now let's take a look at this guy. This is a series circuit also, and the reason I know it's series is because I is flowing through both components. And what we have here is we want to find VR1, the voltage across R1, and what we're being told is that the drop across the diode is 2.1 volts, and this is a light emitting diode, and this is very, very close to being the voltage drop, except it's nonlinear, as indicated here. We'll talk about that in a minute. So when you go to do this and find VR1, is what you have to remember is that the sum of the rises is equal to the sum of the drops. And what we're missing in this case is the voltage drop across R1. So we would simply say that 6.5 volts, which is the rise, is equal to the voltage drop VR1, whatever that is, plus the 2.1 volt drop across the lead, which we know. So all we have to do is solve for VR1, and we find out that that becomes, or that is 4.4 volts. So if we added 4.4 volts to 2.1 volts, of course, we would end up with our 6.5 volts here. So let's take a look at Ohm's law here. here's V, negative V. Oops, got that kind of backward here. This is negative V and this is negative I. And Ohm's law is a straight line which goes through the origin. And what it says is any V1 divided by its corresponding I1, subtracting any V2 from its corresponding I1 minus I2, and let me kind of write that down. R equals V1 minus V2 divided by the corresponding I1 minus I2 is going to be a constant. Doesn't matter where on this line you do it. Quadrant 1, that's fine. If they're both in quadrant 3, that's fine. If you split the quadrants like I did, that's fine. It's a linear relationship. In Ohm, called it K for constant, but we call it R for resistance. Now, if we take a look at a light-emitting diode, it is anything but linear. In quadrant number 1, it's an exponential. So we can't really use Ohm's law in that sense. In quadrant 3, it's just basically the leakage current. M is very close to 0 until we exceed the breakdown voltage, which for a light-emitting diode is about 6 volts. And when it breaks down, things like that happen. Current rises in the negative direction with the negative voltage. The device overheats. High voltage, high current equals high power. Bang. So that's what happens if you break down a device. But over here, what we could do is find the instantaneous resistance, which would be here and here, dividing V by I, but that would only be valid for that point. We could not, NOT, say that the resistance of the light-emitting diode is so many ohms, because it's going to vary. It is not a linear relationship. An important concept to understand. So let's take this one more step here. Suppose that we have 2.2 milliamperes flowing through the light-emitting diode. What's the value of R1? Well, we know that R1 equals 4.4 volts from before, and we just stated that IR1 equals 2.2 milliamperes. And if we go to find R1, as we find out, it's just Ohm's law, which is 4.4 divided by 2. What do I have here? 2.2. Yeah, it should be 2.1, but whatever. Comes out to be approximately 2K. So that would be the value of R1, which basically would limit the current in the light-emitting diode to about 2.2 milliamperes. Now, while I'm here, light-emitting diodes have to have something limiting current. Why? Because of the curve goes way up high on current. And if a light-emitting diode ever starts to change color, flip the switch off. It's overheating. So finally, let's find the power of the lead, and we can do that kind of simply. We could do V times I, why not? We know the voltage drop is 2.1. Up there I said, yeah, 2.1. Current's 2.2. Multiplying together, we get 4.62 milliwatts. And the power of the resistor would be 4.4 volts times the current flow, 9.68 milliwatts. And if I wanted to, I could do V squared over R, 4.4 volts divided by 2K, 9.68 milliwatts. So there's a number of different techniques to solve for circuit parameters. The only question is which one is the easiest to use? And it shouldn't be based upon it's the only one you know. Now we get into a situation, and I call it series with parallel, and the reason I call it that is because series parallel circuit analysis is different. So let's just take a look at this. Here we have basically a series circuit. We're going to have conventional current flowing out around a loop like this, and do notice I have two ground symbols here. That means that this point and this point are electrically connected together. So what we have here is R2 and R3, and these are in parallel. And the way we define that is, if one lead of one part is connected to the one lead of the other part, and the second lead of the first part is connected to the second lead of the second part, they're in parallel. Notice that in a series circuit, One lead is connected to one lead, but the second lead is not connected to the second lead. That's for sure an indication that it's a series arrangement. So to solve this guy, what I would do would be to solve the parallel combination yet that we don't know how to do, call it our equivalent, and then what we're dealing with is a series circuit. If I elected to call this VA, and I elected to call this guy B, so I have nodes A and B, the voltage at A minus the voltage at B would be the same across the equivalent resistor. Thus, if we assign a voltage to the source here, say 6.5 volts, in both cases the voltage drop across R1 would simply be 6.5 minus whatever the voltage is at node A. Okay, so what we've done here is decompose these, and as you can see, we simplified the circuit. Now, we don't know how to do that yet, but nevertheless. Last, let's take a look at another circuit here, and here I've elected to make it a negative supply, and it's good to switch these around. What's really a good thing to do from time to time is to draw the source on the right side. Most books show it on the left. The circuit analysis works no matter where you draw it. Left, right, upside down, other side of the sheet of paper, whatever. So in this case, what I have to remember is that conventional current flow is going to flow out of the positive terminal of the battery, go through these resistors, and I see I have a path of current flow around in a circuit, around in a circle, and I put down the voltage drops across the resistors. So again, this is a voltage rise because the current is flowing negative to positive, a drop, positive, negative, a drop, positive to negative, and a drop, positive to negative. So what we know is that the voltage drop across these three parts has to equal our source voltage. And to make the math easy, I assigned this 3 volts and said that R1 equals R2 equals R3 equals R4 equals 1K. So you can see by this linearity principle that the voltage drop across R1, R2, and R3 are each going to be 1 volt. But what about R4? What's going to be here? What's VC going to be? Now you see dangling resistors occasionally, and you see them in problems, because in the real world you don't want to do that because you waste a part. Not only that, is you waste printed circuit real estate. But the way to handle this is to note this. It's an incomplete path. There's nowhere for the current to flow when it gets here. So the current flow through this I is going to be 0 milliamperes. So what's the voltage drop across R4? Well, V is equal to I times R, and since I is 0, the answer is 0 volts. Now, I use the word voltage drop, D-R-O-P. When I say that, that's the voltage across the resistor. If the drop is 0, that means the voltage on one side is equal to the voltage on the other side. Continuing, let's look at another situation, and this may look like a lot of stuff on this board here, but bear with me, I'm going to be going somewhere with this. Let's take a simple circuit here fed by 120 volts DC, and actually all of this applies to AC also. And we're going to go through a circuit breaker here, as we would have in a typical house, through a switch, we'll say on a bedroom wall, and then a ceiling light, which is a 60-watt incandescent. Lead CFLs does not apply in this example. We'll say that the on resistance of the switch is 1/10 of an ohm. It's 2 pieces of metal contacting each other, so it's going to have some resistance, and that the off resistance of the switch is 100 megohms. The 2 pieces of metal are separated. However, there's still leakage around this through the insulator, bakelite or plastic or whatever, that's supporting the switch housing. So in our circuit here we have 60 watts and 120 volts, and let's start out first by finding the resistance of the filament. So what we know is that the power equals voltage times the current, and then we're going to kind of derive a formula for that to find the resistance. We know that the current is equal to the voltage divided by the resistance, and now if we substitute in V divided by R for I right here, is what we see is that the power would be equal to the voltage squared divided by the resistance. So if we now solve for the resistance, get him all by himself, we see it's the voltage squared divided by the power, 120 volts squared divided by 60 watts, and that gives us a filament resistance of 240 ohms. Now, in a real incandescent lamp, it's a tungsten filament, and tungsten is a metal with the highest melting point, and it's very nonlinear with temperature. So in this case, we're specifically setting this up for a perfect condition. So let's find out what the current is when it's on. Now when the switch is on, it's going to be closed, and we're going to have 0.1 ohms in series with the circuit. And this may seem like a trivial difference, but bear with me. So the current on is going to be equal to the voltage divided by the total resistance, because this is a series circuit. That would be equal to 240 ohms of the light bulb plus the 0.1 ohm of the switch, which will give us an on current of 499.8 milliamperes. So it's a little bit off the theoretically perfect half an amp. So let's find out what the current is when the switch is turned off, and off means that there is no connection here. The switch contacts again are apart, and this will be equal again to the voltage divided by the total resistance, and in this case we have a whopping 100 megohm resistance of an opened switch plus the 240 ohms of the filament, which is very, very low by contrast. And then dividing this out, as we see, we have 1.2 microamperes, 1.2 millionths of an ampere. So finally, getting down to the business here, the voltage when the light on, as we're going to be using voltage divider here, 120 volts, and in the numerator is the resistance for what I want the voltage across, 240 ohms, and then in the denominator we have 240.1 ohms, and that gives us a theoretical of 119.95 volts. So it's very, very close to the 120 supply voltage. Now, what's the voltage drop across the switch? Well, as you can probably guess, it's going to be pretty low. So we'll use voltage divider again, except in the numerator we have 0.1 ohms, and that comes out to be 50 millivolts. So if we were to take a voltmeter and go across the switch when the circuit's on, we would measure about 50 millivolts. Oh, and CB here stands for circuit breaker. Now let's do the opposite on this here. Find out what the voltage is across the light when it's off. Now I have 120 again using voltage divider. In the numerator is the guide that I want the voltage across, 240 ohm filament resistance, divided by our total as before, and this gives us 288 millivolts. So that would be very low, and the light, for all practical purposes, would not at all be on. But what's the voltage across the switch? Well, again, voltage divider 120, and in the numerator we have the 100 megohms, which is the resistance of the switch when it's turned off, again divided by our total, and that voltage across the switch comes out to be 119.99 volts. Now, what that means in reality is that if the circuit's turned off, and here are the two terminals on the switch, is if I were to take my fingers and touch them like this, I would be across 119.99 volts, and I most certainly would feel like it. Feel it rather, in a relatively unpleasant way. I've had a number of shocks. I never like them. So the point of this is, if you turn the light off, does not mean that the circuit is de-energized. What you have to do is get down and open the circuit breaker. That means probably some clocks in the bedroom are going to have to be reset, so on and so forth. But you don't take chances by playing with live wires, especially if it's in the voltage range that can, well, how should I say, kill you? So across this here, as I've shown here, I've got my fingers here, and that's going to hurt, but it's not going to kill me. And the reason is that the current flow is simply going to be through my hand like this. Now, if I were to touch it like this, say when I was working on it with a screwdriver, different story. Current now flows through my body, crosses chest cavity with your heart. Bad things can happen, especially if it's AC, because AC is more dangerous than DC. Another measure, if I'm outside, say standing on a garage floor, and I don't know what the moisture content of the concrete is, I might have a partial ground, and this is a ground symbol here, back through my body to the voltage source. So once again, in outside it's even more dangerous because all you need is one point of contact on your body, and the other basically is something you're not aware of, which is your feet. So once again, open the circuit breaker, unscrew a fuse, whatever. Be safe. Last point. You have two switching wiring arrangements. One is called a high side switch, and this is typically what you'd expect a circuit to look like. We have a voltage source here, and I'm just using perfect parts, perfect switches and loads and so forth. And 12 volts here, and we're connected across our load. Maybe that's a light bulb, maybe some electronics, who knows, don't care. And I'm going to make a measurement at this point. So when the circuit is off, what I'm going to measure here is 0 volts. Why? Well, there's no path of current here. And since the current here, I, is 0, I times R, which is going to be the voltage drop, DROP, across the resistor, is going to be 0 volts. Hence, if I take a voltmeter and measure between these 2 points, I will see 0 volts. And, contrarily, if the circuit's on, shown by this switch, I am going to have a current flow, I am going to have a voltage drop across the switch, and since we're not including any resistance of the switch, that would be 12 volts as you would suspect it to be. Now, we also have low side switches, and surprisingly, in general electronics, this is more common than high side switches. High side in commercial power is almost always the case. Like in your bedroom, you're going to be switching the hot lead, which would be the black wire, or a red wire. And in electronics, black is usually a ground lead, not so much in commercial. So you've got to be careful of that. So let's take a look at this. Here I have the switch between the ground and the load, 12 volt source again, and now I have the switch open. And what I'm going to measure at this point is 12 volts. So many times people think that that circuit's on. Let's figure it out here. I have it open, so the current flow through this I is going to be equal to 0. The voltage drop across the resistance is equal to I times R. 0 times any value of R is going to give a 0 volt drop. The drop, DROP, across this resistor is 0 volts. What that means is that the voltage on this side is the same as the voltage on the other side, which is 12 volts. Do note that there is no current flowing through the circuit. This has to be off. But yet I measure 12 volts here. What am I measuring across? The switch, which is open. Sounds like the other page, I hope. Now when the switch is closed, I have a current flow I. Measuring at this point here is basically shorted by the switch itself, so I'm going to be measuring 0 volts. So in high and low side switches, especially low side, the point is because you have voltage does not mean that the circuit's actually on. Okay, so something to keep in mind. That'll conclude, and thank you for watching.